So, let's talk about a huge problem facing science today. Just too much information. There is a literal tsunami of research published every single year. So how do scientists stay afloat? We're going to break down a really cool new framework designed to do exactly that.
I mean, think about it. With millions of papers coming out, how can any researcher possibly synthesize all that knowledge? How do they do a review that's thorough, that's transparent, and that other people can reproduce when they're basically swimming in data?
And yeah, this isn't a problem that's getting any smaller. The sheer volume of scientific publications is growing exponentially. This makes the old way of doing things, trying to read everything on a topic, pretty much impossible. It really is like trying to drink from a fire hose. Well, for a long time, the go-to tool for trying to organize all this research actually came from a totally different field, clinical medicine. It's a tool that was built to answer very specific questions about people's health.
It's a framework called PICO. That stands for Population, Intervention, Comparison, and Outcome. And look, for what it was designed for, it's absolutely brilliant. It's perfect for asking super focused questions like, for adult patients with diabetes, does this new drug compared to a placebo actually reduce blood sugar? See? Very neat and tidy.
Okay, but here's the catch. What happens when you take that super specific clinical tool and try to apply it to something as messy and complex as environmental science? It just doesn't quite fit, right? Is an entire ecosystem a population? Is climate change an intervention? You're basically using a surgeon's scalpel to analyze a hurricane. It's just not the right tool for the job.
And that exact problem, that square peg in a round hole situation, is what led a team of scientists up in Quebec to basically invent something from scratch. They were right in the middle of this massive project, reviewing all the ways people project water demand, and they just hit a wall.
So they're in these brainstorming sessions, and suddenly, bam, they have this aha moment. They just completely reframed the way they were thinking about the problem. And this quote right here, this really captures that moment. They stopped thinking about patients and interventions and started thinking about systems and troubles and responses.
And that little shift in perspective, well, that was the birth of STAR. It's a brand new framework built for the messy reality of environmental science. It stands for System, Trouble or Treatment, Alternative, and Response. The language itself is just so much more intuitive for talking about the natural world.
Okay, so that's the big idea, but how does it actually work in practice? Let's take a look at the blueprint for using the STAR framework on a real research problem.
It really breaks down into this super logical four-step process. First, you start big. What's the system we're even looking at? Then, you get specific. What's the trouble? The thing affecting it. After that, you decide what response you actually want to measure. And finally, you think about an alternative you can compare it to. It's just a clear path from a huge topic to a question you can actually answer.
Let's go back to their original case study, that water demand project. You can see exactly how this works. The system, that's the agricultural and city sectors. The trouble, things like climate change and population growth. The response they were measuring was water demand, and the alternative was a bunch of different scenarios. Suddenly, organizing your keywords for a huge literature search becomes way easier.
And because you have that super clean structure, it lets you build these crystal clear research questions. You can literally see how the pieces, T, S, and R, just slot right into place in a question like this. No more guesswork. It gets you to the heart of the issue, fast.
Now this is the really cool part. STAR isn't just for water management. That was just the beginning. Its real power is how crazy versatile it is. Because the words system, trouble, response are so intuitive, you can apply this framework to dozens of different fields.
All right, let's look at precision agriculture. The system? The farm. The trouble, or maybe treatment is a better word here, is all this cool new tech, AI, IoT, robots. The alternative? Just regular old farming. And the response you're measuring is whether yields go up or if it's better for the environment. See, it just makes sense.
Or how about coastal sciences? Same idea. The system is the coast itself, the beaches, the marshes. The trouble is obviously sea level rise and big storms. The alternative might be building a giant seawall, or maybe doing nothing at all. And the response is what actually happens to the shoreline. It just clicks.
So when you put it all together, what do you get? Well, STAR has some major advantages. It's flexible, it's designed from the ground up to think about whole systems, and the language is just plain common sense. But maybe most importantly, it makes the whole research process more transparent and easier to reproduce. And in science, that is the absolute gold standard.
But this isn't just about making things better today. This new way of thinking could be a launch pad for what comes next.
I mean, by creating a structure that's so logical, a structure that a machine could understand, you open the door for some really powerful new tools, and the creators are already thinking about that.
Which brings us to a really mind-blowing final thought. The team that created STAR is already thinking about this. What if you could build a generative AI on this exact philosophy? Imagine an AI that could help us ask better questions and search that vast ocean of literature using this kind of structured, big-picture thinking. Now that will be a game changer for taming the research tsunami.